Welcome back to ECE 442-542. This is the review session for exam number 1, and I'm not going to go over the exam process. If you've been here, I'll just sort of show it to you on the screen. You can read it for yourself. There's some things that you can bring, basically 2 pages and a calculator and something to write with. Don't bring a textbook, a cell phone, a computer, class notes, and we'll be ready to go. What you can start preparing for are topics that are listed on the D2L site for the exam number 1 class or period of time. And there's also practice exams, and some of those exams might be for semesters in which topics are shuffled relative to what we have covered material. So pay attention to specific problems. There may be problems from old exams that we aren't going to be worrying about on exam 1. We might be worrying about those in subsequent exams, or maybe not at all. And hopefully I've indicated which exams to examine or throw away on old exams. You also will be responsible for the material from homeworks 1 and 2 and material up to today's lecture, or the lecture on the 5th of February, which was just completed. If you like to dance, then you should be fine with this. We're dancing around a square. Square dancing. You should be able to go from difference equations to transfer function, or from a transfer function to difference equation by a straightforward Z transform or inverse Z transform without worrying about initial conditions. And that's fairly straightforward. You just have to keep track of this Z to the minus 1, or Z, as an operator and use it appropriately. We'll work through an example of how you can find a block diagram from difference equations, but you should be able to do that. Once you're given a block diagram, you should be able to label the outputs of the delay blocks as your state variables, and that now the number of delay blocks gives you the order of your system, or how big your state vector is going to be. And these notes hopefully will be made available to you, so you don't have to copy down this first part. This first part I'm going to sort of quickly go through. It's a summary, and then we'll slow down a little bit and walk through an example that helps illustrate most of these concepts. And you now have a state space representation from a block diagram. You can find via this formula, this algebra, matrix algebra with a complex variable Z, how to find the transfer function capital G of Z once you have your system described by a state space representation. One of the nice things about that direction, going from state space to transfer function, is it actually gives you a way to check your state space. We could have 20 different state space representations for exactly the same system, and they may not be equal states, the same state space representation. They will be equivalent, and if all of you computed the transfer function and you didn't have any mistakes, all of your transfer functions should be the same, even though your state space representations may not be equal to each other. They would be equivalent, but now I'm making a distinction between equivalent and equal. Given a difference equation, you should be able to find a solution of the homogeneous part of that equation, which means you set the input to 0 and you're really just looking at what happens if I have non-zero initial conditions, how does it evolve in time? Or if you now have a difference equation that's driven or forced or excited by a particular input, can you combine the forced input solution, which is what we call the particular solution, with the homogeneous solution to get the complete solution? And when I speak of structure of the output, and you could do that for either the homogeneous case or the forced case, the unforced would be, how does this system naturally like to shake? What are the roots of the characteristic equation? That gives you the natural modes. The forced is the natural modes plus however you're shaking that system. What are the modes that you're shaking it with? And if I'm just asking for the structure, you don't have to find all of the exact coefficients. You can leave it in terms of unknown coefficients, but I do need you to tell me the R values, the theta values in exponentially damped sine waves or exponentially damped cosines, or how is it collapsing exponentially. I need that information, but the weighting on those terms, I don't care when I just ask for the structure. You should be able to find the sampling frequency or the sample period given a system, where that system now might have a particular highest frequency, or what I've been calling a closed loop bandwidth, which doesn't necessarily make sense until we start talking about closed loop or feedback, but it's really the fastest dynamics in your system. You sample 30 times that. That's our rule of thumb. Where the sampling frequency could be in terms of radians per second. That's omega sub s. It could be in terms of hertz or cycles per second or samples per second. That's f sub s. Or you could talk about how fast you're sampling by giving the sample period, which is seconds per sample. And all of those can be set equal to, by the rule of thumb, this 30 omega sub s. So this is our rule of thumb. I'm giving you the answer, actually, but here, let's say, what's the order of this system? This is a continuous time system. It has a transfer function, capital H of S, and that H of S has poles associated with each of these x's. What's the order of that system? And now it's as simple as how many x's are on the board in this portion of the screen. And if you have one that's above the real axis, you need its twin or its conjugate below the axis. If we have real coefficients in this transfer function, our poles and zeros, for that matter, appear in conjugate pairs. For S sub 3, we have an S sub 3 bar, where that means it's the complex conjugate of S sub 3. We just change the sign of the imaginary component. If we had an S sub 2 upstairs, we have an S sub 2 in its mirror image downstairs. That gives us 4. We have a real pole at S sub 1. We have 5 poles. This is a fifth order system. We now have behavior influenced by all 5 of those poles moving together. Obviously, S3 shake at a particular, they have a damped frequency influenced by how far away from the real line they are, but they also have a particular component of damping influenced by how far into the left half plane or what their real part is. Sigma sub 3 then indicates how quickly they are damping exponentially. Omega sub d tells us how they're shaking with frequency. And actually, we want to know more about their natural frequency, which is the combination. It's the hypotenuse of that real part and imaginary part. We really want to know what is R sub 3, or what's the magnitude of S sub 3. That's what we will use to determine which of these sets of poles or groups of poles do we need to concern ourselves with when we pick a sampling frequency. What I'm suggesting here is if you had a circuit that had 5 energy storage elements, you would have 5 poles. You've now found this transfer function. You've found all 5 poles and you've sketched them, or you have them mentally, or you've written down where they are in the complex S-plane. You now have 5 poles, 2 pairs are complex conjugates, and you have a real pole. Now you want to know which of these do I use, or how do I use all of this information to pick a sampling frequency. And I'm trying to also give you a little bit more insight. S sub 1 is the pole in the S-plane that's closest to the origin. That's actually the slowest pole. That will dominate, so that exponentially decays much more slowly than the poles at S sub 2 or the poles at S sub 3, just because of their comparative distance into the complex S-plane, their real component. The exponential damping on S sub 3 is slower, so it will last longer. It dominates the response. That's what we mean by what's the dominant pole in this system. It would be S sub 1. Contrast that with the fastest pole. Which ones are, and here fastest really needs to take into account not only its exponential decay, but also its shaking. You could have something that's really exponentially quick in decay, but doesn't shake very much, oscillating, and you could have something else that shakes a lot and doesn't have much decay. Well, you need to make sure that you're sampling consistent with those two compared to one another. And how do you compare them? By looking at their hypotenuse, or their radial distance from the origin. You would try to find the one that's furthest away from the origin, and that's going to influence. In this class, we'll just agree that we find the largest hypotenuse, and that's the one we use to determine omega sub s with our rule of thumb. Is that clear? Here I've tried to actually sketch it so that you can visually see that the magnitude of S sub 1 is bigger than the magnitude of S sub 2, and that's bigger than the magnitude of S sub 1. And if that's the case, then what do we use for omega sub c? Our rule of thumb says omega sub s is dependent on omega sub c. Omega sub s is 30 omega c's. What's omega sub c? It's 2 pi f sub c. Yeah, you're kind of trying to get extra credit. It's 2 pi f sub c. It's 2 pi over t sub c, but we want what is omega sub c. We have that information here. It's the fastest, and I've actually labeled it Have I not? Isn't it the magnitude of S sub 3? So we find the hypotenuse of S sub 3, and that's now what we will use for omega sub c. We use this combination of sigma and omega sub d. It's the natural frequency of that set of poles. And once you have that, then you could say, oh, 2 pi over t, which is omega sub s, is 30 omega sub c. So that in this case, omega sub c was the magnitude of S sub 3. We now have t as 2 pi over 30 magnitude of S sub 3. And this is this square root of sigma sub 3 squared plus shouldn't try to draw really, really tiny. I can't. But that's the distance away from the origin of that pole, either the one up above or one below. They're the same distance away from the origin. That's how you would find the sample period. In this class, we're concerned with bounded input, bounded output stability. That means if I put in a bounded input, I want to have a bounded output or the system is not considered stable. And that means that I need all of my poles in the complex z-plane of that system to be strictly less than having their magnitude has to be strictly less than 1. They have to live inside the unit circle to be bounded input, bounded output stable. Otherwise, if they were on the unit circle, I could actually find a given signal that's bounded that would cause the output to go unbounded. And here is a visual of that. And it only takes one bad apple, one pole outside the unit circle to cause the whole system to be unstable. You could have 1,000 stable poles or 1,000 poles inside the unit circle, one outside, and boom, that whole thing is unstable. On the left, what's the order of the system? Your left. What's the order of the system on your left? Fifth order. You're just counting x's. What's the order of the system on the right? Your right. Third order. But do you see why the left is stable and the right is unstable? Equations of motion. When you get out and you're working, you should be able to analyze all sorts of circuit or systems. Be that a circuit, a mechanical system, an electromechanical system. You had the opportunity to look at an electromechanical system on homework number 1 with this DC motor. There you applied some power electrically and you were spinning something mechanically. It's an electrical, mechanical, and electromechanical system. On the exam, we'll probably focus on a circuit problem. That's what the 2 red lines mean, underlined. So you now have an advantage over anyone that just looks at the notes, and you don't have to tell them otherwise. Pardon? They have the video, but I'm guessing some of them speed it up so fast they won't even hear this 3-minute discussion of why those red lines are there. It'll sound really. Z-transforms. There are many different ways of dealing with a Z-transform. One is given a function of little n, this sequence of numbers, x of n. Can you find the Z-transform? Another is if you're given a difference equation. Can you Z-transform that? And typically there we don't even worry about initial conditions. We'll do that more on exam 2, maybe when we worry about finding the complete solution with initial conditions. We need to know the way to do it with the structure on exam 1. And block diagram, we need to be able to go from time domain to frequency domain. Where here is the time domain. The operator Z is the frequency domain. And that's pretty easy. You simply have to erase either the delays or the Z's and replace them with the corresponding. If it's a delay, you just replace all of those delays with Z to the minus 1s. Now we're back to the square dance. Well, we've been playing with the square dance a lot already, actually. I just hadn't been mentioning it. But here, finding that transfer function, you should be able to find it different ways. Either with block diagram algebra, and what's a way to do that? Well, you might focus on the signals coming out of your summing junctions and concentrate on those. But eventually, you just want one equation that contains the transform of the output and the transform of the input. And then you can divide out everything and find the transfer function. You should be able to find a transfer function from a time domain difference equation, a linear difference equation. There you're neglecting the initial conditions. You just Z-transform and you find the transfer function. And if you're given a state space representation, you can compute the transfer function from this formula. That's not so critical, I don't believe, because that really is, given time, I assume you can perform this linear algebra manipulation. That's not so critical. I want you to know sort of this connection between all of those. And so if you're running short on time and I ask you something like this, you could just write this down. But eventually you would have on your crib sheet maybe a transfer function state space representation, and you could actually just by inspection go between the two. And we'll become more comfortable with that as we move through the semester. Settling time determination in the Z-plane. We focus on one equation, so we're approximating all of these poles by one pole. What's the order of this system? In the center of your screen. Doesn't have to be left or right. Now you can probably find that on one hand, right? It's fourth order. You had 4 poles. What R do you use? Which R do you use to find the settling time? Here we're wanting to know, what is capital N? How many capital N's will it take, or what's the value of capital N? How many contractions on R will it take for y of capital N to be 1% of y of 0? That's what we're meaning by the settling time. If that's the case, it hinges on picking an R. Which R do we pick? And these are supposed to be conjugate pairs. So the x's in the first quadrant are paired up with the x's in the fourth quadrant. They should be mirror images. So R sub 2 corresponds to both of those poles. They're the same distance from the origin. R sub 1 is paired up with the 2 on the right. Can you tell me anything relative to those pairs, how they compare? If I highlight this one, that pair, and I highlight this pair, can you tell me which pair would be the fastest pair? Yellow or blue? Which pole is the fastest? How many think it's blue? How many think it's yellow? Why do we think it's yellow? So now I'm saying fastest and dominant. Are those the same? No. So I could have asked you which one's the dominant, and that's the opposite of saying which one's the fastest, isn't it? So now if you can find the fastest, the other one's the dominant, right? So now we need to figure out which one's, what did I ask, the fastest? Which one's going to collapse quicker? That's the fastest. So now if you, let's just put some numbers on this. Let's say R sub 1 is 0.8, and let's say R sub 2 is 0.4. 0.8 squared cubed to the fourth. How does that compare with 0.4 squared cubed to the fourth? Which one's getting quicker or getting smaller faster? 0.8 or 0.4? 0.8 squared is 0.64. 0.4 squared is 0.16. Which one had the bigger collapse? The 0.4? The ones closest, now think of a bullseye. You could just start putting circles here. And now we want to worry about this bullseye. And what do you typically want to do when you look at a bullseye if you're in target practice? You're trying to go for the center, right? That's the fastest. The ones closest to the origin are the fastest. The ones closer to 1 are dominant. What? Pardon? Oh, here? So this is the S-plane. Oh, come on, come on, come on. This is the S-plane. The other is the Z-plane. Z is equal to e to the st, right? So we are going to get a little difference here. And that's why we have to, that's why you came to the review session, right? So you won't mess this up on the exam. You can mess it up all you want now as long as you get it square in your head by Wednesday. These are you get far out into the left half plane in the S-plane, and it's really fast, isn't it? Because you have a big negative exponent. E to the minus 100t. Now, what happens here? We want r to be really small, don't we? To be fast. We want the radius from the origin to be small, to be fast in the z-plane. What happens, so if you forget, go to 1 and say, what happens if I iterate with a pole at 1? I don't move, do I? I'm constant at 1. What happens if I'm close to the origin? If I'm at point 1, I've now already collapsed 10% of what I started with in one time step. 0.1 squared, now I'm 100%. Took me 2 samples and I'm now within my 1% if I started with an R of 0.1. Just plug in some numbers and start getting a feel for, well, this can't be too bad. Let's see, 0.9, look at that one. 0.1, look at that one. Which one collapsed quicker in terms of capital N or number of N? So now, which of these, yellow or blue, are the fastest? Yellow being fastest, show of hands. All right, this is the fastest. This is the slowest. And that one then dominates. That's the one that will dominate because it'll be living longer than the ones near the origin. So now, which R do I pick when I want to apply this formula to this fourth order system? Which R do I use? You want the one that's dominating your response, right? So now you pick, you use R sub 1, that's going to influence the dominant behavior. That's what it's going to take before you, in all of your dynamics, that's the one that you have to focus on as the slow one. That will be the one that you pick capital N with. Remember, z is equal to the e to the st, and in the discrete time we're in the z-plane, in the continuous time we're in the s-plane. And why did we pick the fast one in the s? Then we were worried about sampling frequency. Here we want to know what one dominates. We've already picked a sampling frequency. We now need to know which one dominates. All right. Now we can start walking through a lot of these different examples with one equation. We can take this equation and go all over Tucson. Go all over the topics of exam number 1 material. First, let's find a state space representation associated with this difference equation. Y of n is equal to 1.4 y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus 1/2 u of n minus 2. And this is more like your homework problem where you had delays in your input as well as delays in your output. Unlike the example that we might have done in an earlier lecture where we didn't delay the input. Let's look at one construction approach. And this particular approach, I'm going to assume that I have access to y, the output at time n, and the input u of n at time n. Those I'm assuming are available. I have access to those. And now I want to use capital D not as a differential operator, but as a delay operator. Instead of me writing delay, I'm just going to say capital D. So this is going to be defined as a delay operator in the time domain. Z to the minus 1 is a delay operator in the frequency domain. Here capital D is its counterpart in the time domain. So now what I want to do is actually write the right-hand side. Since the left-hand side is already y of n, I actually want to now try to write the right-hand side in terms of y of n's and u of n's. Without any delays, all the delay will be accounted for or accommodated with my delay operator. Meaning, to generate y of n minus 1, I would have to delay y of n with one delay. Is that clear? To generate y of n minus 2, that has to have passed through two delay operators. Likewise for u of n minus 1 and u of n minus 2. So I'm actually going to pair up my u's and y's with the same arguments. I'm going to pair up u of n minus 1 with y of n minus 1, only pass those through one delay, and the u of n minus 2 and the y of n minus 2, I'm going to pass through two delays. Meaning, I wish I had a bigger screen, but I'm going to try this. Y of n I have. That I'm going to keep on the left-hand side. But now, I'm going to delay 1.4 y times y of n, and that will actually give me 1.4 y of n minus 1. Is that making some sense? I really haven't changed this equation at all by means of using this delay operator. And I can do something similar with u of n minus 1. I can say, oh, plus u of n. And those are just going to pass through one delay operator there. The remaining terms have to go through two delay operators. So now let me put in another delay and a different bracket so that you can sort of follow things bracket-wise. Meaning inside, so do you see that this black delay on the left and this blue delay are now going to operate on what's inside the blue funny brace, whatever that brace is, or bracket. I can now put in here minus 0.45 y of n. And that should be giving me that. This with that and that give me what I need on the right-hand side. I've delayed minus 0.45 y of n through two delays, and that gives me minus 0.45 y of n minus 2. I only have one more term left, so I would be sort of crossing out all of these terms as I go. I have one more, which is this 1/2 u of n. I can close that, and I can actually close the other bracket. so that this particular term now goes through that one and that one to produce that. Is that clean? Now what I want to do, I said I have access to y of n and u of n, and that's all I have up here, and I can now combine these with summing junctions and delay blocks, because that's the only thing that's different besides y of n and u of n in this equation. First, let me create this innermost bracket. Let me generate star. So star is going to be coming out of a summing junction, because that's how I'm combining those. And I'm now saying that I have u of n coming in here, and maybe I have y of n coming in, whoops, from over here. And I want to create star right there. To create star, which hasn't yet passed through the delay, I need to scale u by 1/2. Sorry, I shouldn't have squeezed that in. And this y, I need to scale by minus 0.45. Does that look like I've generated star where I need to generate star? The output of that summing junction better give me minus 0.45 y of n plus 1/2 u of n. That's what I say star is. Then coming out of that rightmost delay block is going to be a delayed version of star, and that's actually going to be, oh, I need another, whoops. I need another color. I want this. That's now right here. That's this signal. Now I want to combine that magenta shade with a u of n and a weighted y of n in a summing junction. So coming out of that arrow to the right is going to be another summing junction. And I'm going to take 1.4 times y of n and combine that with u of n. And that's now right here, which is that mess. What do I want to say that is? Star with a 0. Star with a 0. If we had gold stars, they would be all over on the refrigerator, wouldn't they? You get a star. But we now have star 0. Maybe I should have put a crown on that star. Are we seeing where this is at? What do I need to do with that star 0 to produce the left-hand side? Just delay it. So if I put that through one more delay, what do I have coming out? That's all that I have on the right-hand side is equal to, it was dramatic, I will agree. This is now y of n. So there is now our signal that we needed, y of n, and u of n is our input, and we've generated our output y of n. This is now our block diagram, and how many delay blocks do we have? 2. What's the order of that system? Second order. Now, is it clear where that delay block came from? And you should just go home and play with this. I think you're going to have a lot of fun. You're going to have all these stars and different zeros and bars and x's. You can give somebody a difference equation and say, produce a block diagram for that. Isn't this fun? So you don't need anything more on a Friday night than a difference equation, right? No, I don't see anything funny in that. All right, so here we have a block diagram. How do we find a state space representation? I know, I don't have much of a life, but that's okay. You guys can. How do we find a state space representation? What's the strategy? We've got to have some fun. For crying out loud, it's 7:45 on a Monday night, right? We just label the outputs of the delay blocks as state variables. How many state variables do you expect? 2. So now, do you see the non-uniqueness that could arise? I could label that rightmost delay block as x sub 1. Somebody else might label it as x sub 2. That's fine. But here, if I label this as x sub 1 at n, and this one x sub 2 of n, then I know exactly what x sub 1 of n plus 1 is. That's right here. And x sub 2 of n plus 1 is there. And I have to clean this up. If I'm playing with block diagrams on a Friday night, I have to at least make it legible. So there's my y of n. Or it doesn't have to be that legible if it's a Friday. Never mind. But you have to make sure that this is clear on Wednesday. Now it's a straightforward operation to put this into a state space representation. How big is your system matrix? What are the dimensions on your system matrix? What do you know about the system matrix? Geometrically. If you now were in a geometry class and you were looking at geometrical figures and somebody said, what do you know about the system matrix? What would you draw for them? A square. It's always square, your system matrix. And in this case, it's each side of that square is the size of your number of state variables, which is 2. We can now say that we have x1 of n plus 1, x sub 2 of n plus 1 is equal to, there's your system matrix right there. If it's 2 by 2, you have 4 elements in that 2 by 2 matrix. Here is x sub 1 of n, x sub 2 of n. And how many inputs do you have? Variables, input variables, unique input variables. I could give you 2, couldn't I, on the exam, and it shouldn't be that much more difficult. I could give you 6, and it really wouldn't be that much more difficult. You just have to keep track of them. But in this example, how many unique inputs do I have? 1. So what's the input matrix? Dimensionally. Is it 1 by 1? Is it square? Now you need the input matrix times a single input, which is a matrix that's 1 by 1. You need a 1 by 1 matrix times something, giving you a 2 by 1 vector. So what do you multiply by a 1 by 1 to get a 2 by 1? You can go to Home Depot and ask for a 2 by 1. They, on a Friday night, I've tried it and it hadn't gone over very well. So it needs to be a 2 by 1 matrix. We can now fill those elements. We now have 6 entries to put in to fulfill our dynamic behavior of this system. What's in the top row? X sub 1 of n plus 1. What makes that up? Do you see that? Well, now I would just say, okay, let me look at all of the signals on that summing junction. X sub 1 of n plus 1 is the output. Everything else is presenting itself as an input. That has to be on the right-hand side. So I could just walk around counterclockwise. The top one is U of n, so that comes in with a 1 right here. I have an X sub 2 of n, not gained. Well, it's gained with 1. It's not changed. And X sub 1 of n is 1.4 times X sub 1 of n to give me X sub 1 of n plus 1. Those 3 elements make up my top row of the system matrix and the top row of my input matrix. What about the second row? This is now the star. The output of that summing junction is X sub 2 of n plus 1. I could now find, going counterclockwise, all of the arrows coming in. Those are the inputs. I have 1/2 times U of n. That's in blue, so I'll try to be somewhat consistent. And I have a minus 0.45. What happened to X sub 2 of n? It doesn't directly come in to make up X sub 2 of n plus 1, does it? But it's helping to create X sub 1 of n, which is coming back and making X sub 2 of n plus 1. And those are now my equations that govern the dynamic behavior. This is now my system matrix phi. This is my input matrix gamma. If I want a state space representation, I also need the output equation. How many outputs do I have in this example? How many outputs do I have? Just one. So now I have one output. I should be expecting everything to end up with one row. But I know that I have a state vector that's 2 state variables tall. It's only 1 column wide. And I have a single input. Now I can make my matrices consistent with or compatible with the left side, which is they better end up being a 1 by 1 matrix. The product of something times the state vector plus something times the input vector. The input vector is 1 by 1. What do I multiply a 1 by 1 to get a 1 by 1? A 1 by 1. What do I multiply a 2 by 1 to get a 1 by 1? A 1 by 2. And this is my direct feed-through matrix. This is my output matrix H. How do I populate or put numbers into those 3 blanks? I have 2 blanks in H and 1 blank in J. Now I simply go back to my block diagram and I say, okay, what signals create Y of n? It's just x sub 1. There's no direct connection with the input u, and there's no x sub 2 going in directly to make y. It's just x sub 1 is y. To make that happen, I just say 1, 0, 0. I started with the difference equation on a Friday night, and I now have a block diagram. And it's Sunday. I had a great weekend. Now I could ask all sorts of questions, but the first one I might ask is the system stable? Looking at this difference equation, maybe you couldn't have told, but you could do what? You could z-transform this difference equation and find the characteristic polynomial, set that equal to 0. You have a characteristic equation. You find the roots of that, and what are you looking for those roots to be? Inside the unit circle. Now you have a block diagram. Okay, maybe you don't see it there, but you have a state space representation. How can you find stability in this representation? The eigenvalues of the system matrix, which is this phi. So now we can say, okay, one way to do that is to look at the eigenvalues of phi. Which we can find by solving the determinant of lambda I minus phi, setting that equal to 0, and finding the values of lambda. Those will be our eigenvalues. Those will be our poles. That's how this system naturally wants to shake or move. In our case, how big is I, the identity matrix? It has to be compatible with phi, and phi was square, it was 2 by 2. So now we have lambda and lambda. We subtract phi, minus 1.4, minus 1, 0.45, and you should be able to find the determinant of a 2 by 2 matrix on the exam. That's the product of the diagonal minus the product of the off diagonal. And can you factor that? What are some factors of 45? 5. Oh, 5 and 9. But now we have a 0.45. So if we have 0.5 and 0.9, and 0.9 plus 0.5 is 1.4. So now we factored it. If you didn't see that, no problem. Just plug it into the quadratic formula. It's a quadratic, and it will come out if you do the correct key presses. We now know that we have roots at the values of lambda that cause that to vanish. One such root is lambda equal to 0.9. Another root is at 0.5. And this is how that system, that original difference equation, likes to shake. If you walked up and kicked it, one mode would do what? Are these oscillatory or exponential? Are they complex? Are they real? They're real. So what are these going to do? They're not going to shake, are they? They're just going to kind of exponentially go, shrink, right? Is it stable, our system? Because they have a magnitude what? Since both of these have a magnitude less than 1, we know that our system is stable. Now I could ask you which root is dominant. I'll do the hard part. Lambda is equal to 0 point. Which root is dominant? How do you determine which root dominates? You could sketch them in the z-plane, and which one is the dominant root? The one that's closest to the unit circle. And this, they're real, right? So now you're just looking at which one of those two on the real line is closer to 1. That's the one that dominates, isn't it? I gave you the look. Don't worry about how I give you the look. I could be trying to fool you, huh? So, you were correct. The dominant root is at 0.9. That's the closest to 1. That one decays the slowest. That's the slowest. That's the dominant. What's the settling time? And how now all you have to do is say, oh, it's all in this class, we're agreeing that even if there's 100 poles and they all cooperate and they're all stable, we're just going to focus on the dominant, right? To do the settling time, we have to look at the slowest one. That's the one that's dominating because it takes the longest to get to leave. So the dominant one is the one we focus on, the one that's the closest to a magnitude of 1. And in this case, we then would say, oh, this is what we're using, and we set r to the n times that. So in this case, what is our r? It's the dominant. And here you can hopefully see that those two, it doesn't really matter where we start. We just need r to the n to eventually be 0.01 or less. We need it to be less than 0.01. You could continue to raise r to higher and higher powers, and if you're counting, you can figure out eventually what capital N is. But you can also do it with logarithms. You can solve for n, and we've done that. N is now minus 2, since that's log base 10 of 0.01. Log base 10 of 0.9. And in this case, n ends up being 43. We'd have to hit 0.9 43 times before it gets less than 0.01 of where we started. So it takes a while if you have a pole at 0.9. It takes 43 samples to be finished if we call 1% our settling time. I said that was one way. A second way to do the analysis for stability would be to z-transform that difference equation. If we z-transform the difference equation, We're not worrying about initial conditions because we just want to get the transfer function of our system. We can now factor all of these common terms out, and we have 1 minus 1.4 z to the minus 1 plus 0.45 z to the minus 2 equaling z plus z to the minus 1 plus 1/2 z to the minus 2 u of z. The transfer function is output z transform over input z transform, y over z. That's g of z. That's now z to the minus 1 plus 1/2 z to the minus 2 over 1 minus 1.4 z to the minus 1. And if we wanted to, we could, what? Hit top and bottom with z squared if we wanted to see it in terms of positive powers of z. And we now have z plus 1/2 over z squared minus 1.4z. And there's now our transfer function. And how would you check stability of this system? You look at the poles. And the poles are downstairs. Those are the values of z that cause the denominator to vanish. Those are the poles. The zeros would be upstairs. The values of z that cause the numerator to vanish. We need the roots of z squared minus 1.4z plus 0.45. And we should be getting the same answer. If you wanted to go home and have some fun between Friday and Sunday, you could, what? Find the transfer function with our state space representation, because now you have the answer in the back of the book. You have the g of z. You could find the state space based transfer function. And I'm going to let you have that fun on your own. Was there a question? So now the question, I think, was trying to say, wait a minute, you have a time domain state space representation, and now I started talking about z-plane poles, maybe, or eigenvalues. The eigenvalues are equivalent to the z-plane poles. And we found the eigenvalues of this time domain equation by looking at the eigenvalues of phi. Now, it's a Friday night and we want to dance, so now we just started with a difference equation. Now what happens? Well, we could say if somebody comes up to you and says, what if I excite you with this input? U of n is equal to 0.7 to the n cosine pi over 8n for n greater than 0. What is the structure of y of n? Could you find the way this system naturally wants to move without U of n? Can you find the homogeneous, or what does that even mean? This is now actually the natural behavior of the system. Can you write that down, knowing what you already know? What do you know? You know the poles, you know the eigenvalues. Those are the same. Does that tell you anything? That's exactly what determines the natural behavior of your response. You now know that naturally, if you just walked up and gave this a bump, basically initialized it, and watched it move or respond, that would be its natural response, its initial condition response. You now know that it would look like some coefficient 0.5 to the n plus some other coefficient alpha sub 2 0.9 to the n for n greater than or equal to 0. And that would be the structure of your homogeneous. What's the particular structure? This is actually the response due to the forcing function or functions. So if you had multiple excitations, they all would be contributing their part to the particular solution. I just gave you one. I just gave you, what is this? Is this an exponentially damped or growing cosine waveform? And how do you know? Why is it damped? 0.7 is less than 1. This is an exponentially damped cosine. And you know how it's oscillating. It's oscillating with pi over 8, 22.5 degrees per sample. That's how it's ticking around the unit circle, and it's collapsing with each tick by a fraction of 70%. That's what's happening when this is what you're exciting your system with. And that's going to give rise to a y sub particular of n equaling, and now you don't know, you hit this with a cosine, but it's going to give you a cosine and a sine at the same frequency, some linear combination, or you could say it gives you a cosine with a phase shift. I sort of like to just write down a cosine and a sine of the same frequency. And then you could use trig if you wanted to combine those. But it doesn't matter. You can now say, oh, this is beta 1, 0.7 to the n cosine pi over 8n plus a beta 2, 0.7 to the n sine of pi over 8n. And that's true for n greater than or equal to 0. You now know what your total structure is going to be. It's the combination of your homogeneous and particular. And I'm not asking you to find these alphas and betas. I just want the structure. But you need to give me the 0.7, the pi over 8, the 0.5, and the 0.9. I could care less about the alphas and the betas. Is that clear when I say the structure? So now this is just going to be alpha 1 bar 0.5 to the n plus alpha 2 bar 0.9 to the n plus a beta 1 bar, let's say 0.7 to the n cosine pi over 8 n. And do you see that I could actually have said this is also some offset, maybe there, and that would be equivalent. Or it could be a beta sub 2 bar 0.7 n sine of pi over 8n. Those are the same. You would just have to find gamma and beta 1 bar versus beta 1 and beta 2 in the cosine and sine. Why didn't we leave it in the original names? Because it's going to depend, these alphas, if we just had an initial condition response, those values will be different than if we start exciting the system with a particular. So I intentionally labeled those coefficients differently. The alphas I put bars on. What if I gave you, and I applaud you for your patience, what if I gave you a pole zero diagram? Could you tell me how the system associated with those poles would respond in the time domain? If I now said something like the following, given a pole zero diagram for x of z, what is the structure of little x of n? From that, could you actually give me capital X of z? What's not yet known by capital X of z? This goes back to a question 2 hours ago or more. The alphas or the betas in my pole zero, or in my pole zero form of a transfer function. You don't know that by just giving you don't know the gain constant, but you do know all the zeros in the pole locations if they're labeled. And you could write those down. But now, how would you find the structure for little x of n? Do you know it for the pole at 0.5? Yes, it's just 0.5 squared, cubed. It just shrinks. That's an exponential. What about these complex conjugates at 0.75 plus j 0.25? How do you like to describe those? Will that be a exponential? Will it be an exponential cosine? Will it be a pure cosine? What will that correspond to? One, is it stable? Because if you square 0.75, that's about a half, and add on 0.25, that's definitely not a half, so you're less than 1, right? So those are inside the unit circle. It's collapsing, but because it has an imaginary component, it's oscillatory also. So this is a decay, exponentially damped cosine and sine. How do you find that exponential? What is that? Now think geometry class, or triangle, right triangle. You need the hypotenuse, don't you, of a right triangle, and the angle will give you the theta. So you know the r, that's the hypotenuse of 0.75 plus j 0.25. That's the r. You know the angle, that's the inverse tangent of 0.25 divided by 0.75. Now you know what this exponentially damped cosine structurally looks like together with the 0.5. I'll leave it at that. I think we're done. Thank you. Good luck on the exam on Wednesday.